Hi, I'm Jill Boyce. I'm with Intel, where I'm an Intel Fellow and Chief Media Architect. My role is in the XPU Architecture and Roadmap group in Intel that makes video hardware that goes inside of Intel chips. I'm starting this presentation with a quote that is attributed to Andrew Tannenbaum, which seems very apt for the video codec space. The nice thing about standards is that you have so many to choose from. Having spent my career developing video codec standards and performing R&D to build products using these standards, I think this quote is meant to be sarcastic, but I'm not quite sure since creating new video codec standards means new work for video codec engineers. But it certainly is a challenge for product and service implementers to select which codec standard or standards they want to implement for their products and services. In this talk, I will give a little bit of history and current status update of the video codec standardization activities, but I'm planning to spend the bulk of the time discussing the factors that influence adoption of a video codec in products and services. I'm starting with a slide that gives a little bit of history of the development of video codec standards, which I give to different audiences that are often much less informed than this audience is. So you will already know the names of these standards, but I still included it because it provides some historical dates. The list of standards that have been developed, it shows the new major standards, and then it also shows the extensions that have been made to these standards. Typically, the first version of a new major standard is the one that gets the most implemented. The possible exception to that is AVC's high profile that was developed later has been very broadly deployed. Most major standards have tended to be about 7 to 10 years apart. If we go back to MPEG 2 in '96 and AVC in 2003, HEVC in 2013, and then most recently VVC in 2020. So MPEG and ITUT have been working together to develop these video coding standards for a long time and have developed many generations of video codecs. More recently, on the right side of the screen, the Alliance for Open Media was formed, and it is developing video codecs with a goal of being royalty-free. AV1 was finalized in 2017, and there's work underway for a possible future AV2 that's still in a research stage. The AV1 activity built upon some of the earlier work that Google had done in its own private industry specifications of VP8 and VP9. That was some history. Now I want to give a little bit of a current status update. I'll start with MPEG. MPEG has been reorganized recently as part of the SC29 organization. MPEG has historically been part of the SC29 or ISO IEC SC29 as Working Group 11, along with JPEG has been Working Group 1. But now SC29 has been reorganized and has formed many new working groups and advisory groups. And despite what you might have heard, in practice there's been very little change to how the MPEG standardization process operates. MPEG develops standards in many areas of video, audio, graphics, systems. I'm going to focus on the video codecs, most of which have been developed jointly with ITUT, Study Group 16, in joint teams. Sometimes the names have changed over the years, but it's currently named JVET, or Joint Video Exploration Team, which developed VVC. And so it's part of the Working Group 5 from the list. So JVET has recently had finalized the VVC standard in 2020. So what comes next? The group continues to meet generally quarterly, so 4 times a year. More recently, it's been virtual because of just like this conference is going to be virtual. But what comes next after VVC version 1? So in the short term, a version 2 is planned, and it will have a new extension for VVC called the Operation Range Extension. And it's aimed at primarily higher bit depth including 12 and 16-bit, and higher bit rate operating range for contribution instead of just distribution, which the original profiles were aimed at. So with this operation range extension, new profiles will be defined. Also, there's the VSEI, or Versatile Supplemental Enhancement Information. At the time that VVC itself was standardized, a VSEI standard was also formed that included most but not all of the SEI messages. So historically, SEI messages have been as part of the same specification. In AVC and HEVC, SEI messages were included. But for VVC, most of the messages were put in a separate specification called VSEI, with the primary motivation is they can be kind of maintained separately and can be referenced by other codecs. So, a future codec standard, even you could go back and AVC or HEVC could add support for a new SEI message that's defined in VSEI without having to duplicate the definition and the syntax of that SEI message. So it can kind of help in future maintainability and extensions of the standards. The one exception to the SEI messages being in the separate standard are those related to conformance and HRD. So within the VVC standard itself, those SEI messages were contained. But in version 2, when a new version of VVC comes out in version 2, there will also be a new version of VSEI that adds some new SEI messages. Some longer-term activities are exploration-based. And so there's two main activities that are underway. It's unclear at this point if these activities will be done as extensions to VVC, like the operation range extension is going to be an extension of VVC. So it could either be an extension to VVC or perhaps more likely be early work to be preparing for a new standard, H267, if you will. And in these activities, there's two main areas. There's one on neural network-based video coding. And this activity has a lot of activities, a lot of areas under study. The most active ones are related to loop filters, so filters that are within the loop. Super resolution, where you could code the video at a lower resolution and then do a AI machine learning based upsampling to improve the quality. And then there are even some end-to-end machine learning based intra-coding approaches being studied. Also being studied are enhanced compression techniques using what we'll kind of call traditional approaches in terms of not being machine learning based. And there's been an enhanced compression model, test software that's been created that has been demonstrated to show 11% bitrate reduction versus VVC's VTM reference software, but with a pretty significant increase in encoder and decoder runtime of about 4 times the runtime. So this is a promising area to be showing 11% bitrate reduction. It seems that as we go on, video codecs, it's getting harder and harder to get those coding gains, whereas traditionally we've aimed for a 50% reduction in bitrate as you go from codec generation to codec generation. That is getting harder and harder to accomplish. And now an update on the Alliance for Open Media, or AOM side. So what comes after AV1? AV1 itself isn't the only standard that AOM, or Alliance for Open Media, has developed. There are several other existing specifications. There were wrappings to do AV1 in the ISO-based media file format. There was AVIF, or the AV1 image format. And there was ID3 timed metadata. But AV1 has been the only video codec. But AOM has multiple active working groups. The video codec work group is the one that's developing the actual video codecs and studying, and it's currently in a research phase studying new coding efficiency tools. and they are targeting an eventual new AV2 standard, but at this point, a timeline has not been developed. There are also working groups called the Software Implementation Workgroup and the Storage and Transport Workgroup. In the Software Implementation Workgroup, they're focusing on optimized open source software codec implementations. And there's been an initial focus on an encoder that's called the SVT AV1, which some of my colleagues at Intel have been very active in. In addition, the Storage and Transport Formats Workgroup was formerly called the Metadata Workgroup, and it includes time metadata, synchronization, content protection activities. Charters the charters for these workgroups can be found on the link that's shown below. As a video codec standardization person, I've loved this codec about standards for a long time. I won't read through it. I'll give you a second to read it on your own, but I think it's as every time we find a problem with existing standards and decide we want to do something more, then we end up with yet another codec standard. So now I'm moving to the section of the talk where I want to talk about some of the factors that influence adoption of a new video codec standard. So AVC, HEVC, AV1, VVC will be the main ones that I talk about. To prepare for this presentation, I did a little research of what has been published in terms of deployment and adoption of video codecs in the industry. For the last few years, Bitmovin has conducted an annual survey of video developers. And so I'm summarizing some of the results from its 2019 and 2020 surveys. For the 2020 report, they surveyed 792 video developers and industry experts from 87 countries. So let's look at the chart. We'll start with the 2019 one. And so the bar chart, the bar itself, is basically a response to, is your company using this particular codec? And the numbers add up to more than 100 because a service might well use more than one codec. And then in the line that's shown is whether or not you're planning to be implementing this codec. So if you look at 2019, you can see that H.264 or AVC is definitely the dominant codec at 91%. And then it also says 16% are planning to implement. I'm not quite sure how people interpreted the question, because I would think that meant people who are planning to implement that have not already implemented, and then it's greater than 100%. So I think we can't be quite sure how to interpret these results, but it nonetheless gives us some sense. So if we look at 2019 to 2020, so AVC, 91% both cases stays very dominant, widely adopted. If you go to HEVC, which is the next most popular in both cases, the actual adoption rate is actually pretty flat. It goes from 43 to 42%, which just sounds like noise to me. But if you look at the number below of the percentage that are actually planning to implement it in the next 12 months, we go from 32% to 47%, which is then showing an increase in acceptance or plans to be adopting HEVC. MPEG-2 has actually, the usage is also reasonably flat, maybe slightly down from 29 to 27. VP9, pretty flat, 11 to 12. AV1 has a pretty significant increase, going from 7% to 11%. VVC is not included in this survey because it's too new, having just been finalized in 2020. Another recently published study was done by Research TV, which issued a research report with some forecasts about video codec adoption. A lot of the information is available in the free executive summary, which is listed below here in the footer. This is just a survey forecast, and I'm not endorsing it, but I do think it's interesting. One of the things in particular interesting, I think, is showing AV1, here is this curve here in black, I'm sorry, AVC rather, this curve here in black, and how it's still very dominant, but you see kind of over time. So this survey shows from 2020 to 2030. And what it's showing on the y-axis is the kind of workload, the percentage of workload. So this differs from the previous slide, which just said, are you using this codec at all? Instead, it's like, what percentage of your workload is actually using this codec? So AVC is still dominant, not quite as dominant, as we'd seen in the earlier slide, but it's showing kind of over the next 10 years an expectation of it having a steady reduction. This forecast also shows HEVC having a kind of slower but steady adoption. AV1 with the blue curve here starting out lower as just as a smaller percentage currently in use, but showing and increasing at a faster slope over time. And VVC in red showing, basically at the beginning, of course, has nothing, and showing a bit of an uptick at the end. MPEG-2 still exists there, and it's also forecasting the new AV2 standard will start getting will actually be standardized and start getting some adoption there as well. So what are the factors that affect the adoption of the new video codec in products and services? So for services, they need that products be available. If there are no encoder and decoder products that support a codec, then obviously they can't launch a service using them. And typically the services are not the ones that are not always, well, sometimes, but not always building the actual encoder and decoder products. So for products themselves, we have both hardware and software products. Hardware products typically require much longer to develop. Typically, 1 to 2 years, in fact 2 years more likely, after the finalization of the standard to when you first see products. But that's just the early products. To have more broad, widespread deployment in products takes much longer than that. Software products can have a faster rollout because they're not subject to the same constraints and timelines that hardware product development has, but they are generally going to have a lower performance. And when I use the word performance, I mean like throughput or pixel rate. Can it support 1080p or 4K or 8K, and at what frame rate? And so software products generally are going to have a lower performance, and they're going to require much more power than a dedicated hardware product would. As I said, I work at Intel, and Intel is, happy to have you, big Intel is happy to have you both do software and hardware activities for doing codecs. I'm in the group that does hardware, and if you have a dedicated hardware decoder that's, say, running on your laptop, you're going to use a lot less battery and a lot less power than you would if you were using the CPU, a general purpose CPU, to encode in software. It's also the availability of a codec implementation in browsers and operating systems is also very important. This slide shows a little bit of information about codec support in platforms, including browsers, mobile phones, and mobile phone OSs, and then over-the-top devices, smart TVs. So you can see that AVC support is pretty universal. It's in browsers, both in pretty much everywhere, and on iOS and Android, the major phone OSs. HEVC does have support on iOS and Android. It has not been as default activated in all of the browsers, so Safari and Edge do have support for it. It's been pretty universal in the more recent devices, smart TVs and OTT devices. Generally, anywhere that's wanting 4K or HDR has added support for HEVC. VP9 has a fairly broad deployment as well in a lot of devices and in browsers. And AV1 is the newer codec that's been deployed. It's got pretty good browser support across Chrome, Firefox, and Edge, but it's missing Safari, and it's supported in Android. And we've started to see it in some OTT devices and TVs starting in 2020. VVC is too new to have data like that included here. Here are some more details about where HEVC has been announced in products and services. Gary Sullivan, who's one of the two JVET chairs and the new chair of SC29, updates a document every JVET meeting with a status update on the adoption of HEVC in products and services. So HEVC has actually been very broadly deployed in products. Broad product adoption starting in about 2015, following the 2013 finalization of the standard. Again, devices, personal computers, mobile handsets, essentially all 4K UHD television, and include HEVC supports in 2015. We have open source software encoders in multiple OSs. There have been a number of camera deployments that have been announced. Pretty broad support in video editing software packages, and some services, although services have lagged compared to the product support. But there have been announcements with broadcast and streaming services, especially for 4K and HDR. On the bottom, you can see the link where you can find this actual document, which has a lot more detail than what I've shown here. For AV1 deployment, we don't have a single document to point you to like the Gary Sullivan's list for HEVC, but there was actually a panel I had hosted last year at IBC, a virtual panel discussion that talked a little bit about deployment. But anyway, I've gathered a list myself of some of the ones that we've seen announcements for. So for services, we've seen YouTube announced, and Netflix has announced the use for Android streaming. There have been multiple hardware decoders announced. Intel, the group I work on at Intel, has done an AV1 implementation. MediaTek, Broadcom, Realtek, NVIDIA, these are just some of the ones I've seen. I've probably missed some. It's a software decoder, the David software decoder. Television, there's been a number of televisions and set-top boxes that have included. Mobile phones have been a couple, but has not been at this point yet the most widely used mobile phones. So not broad mobile phone deployment yet. There's open source software. I mentioned earlier this SVT AV1 that's done by the software implementation work group that is a more optimized AV1 encoding, so can make better use of CPUs to have high quality and faster encoding. And then there have been a number of encoder products, including FPGAs, and there's been support for OSs in Windows 10, in Chrome, and in Android. Let's move now to VVC, the newest of the codecs. So Gary Sullivan has also started providing a document with announcements of VVC implementation and deployments. VVC is very new, so the number of product announcements is obviously going to be much smaller than for HEVC and for AV1. However, I think that there's been a quicker pace of announcements that we've seen in the past. A particular note is this open source video encoder, VVenC from Fraunhofer HHI, which has been made available really quite soon, within a few months after the announcement of the deployment of HEVC, of VVC. In addition, there's been some demonstrations and some software from software decoders and some demonstrations. An encoder product, Bitmovin has announced a product based on using the VVenC, and then the bitstream analyzer. Typically, One of the most compelling reasons for services to adopt a new codec is because it enables some new usage that wasn't possible before with the earlier generation codecs. When MPEG 2 first came out, it was really instrumental in enabling digital television. So like DirecTV Satellite was a very early MPEG 2 adopter. And now all of digital television, satellite, cable, DSL fiber, etc., all use digital television. MPEG 2 also helped enable DVD playback. For AVC codec, high definition television or HDTV and mobile phone usages were really new usages that AVC enabled. MPEG 2 wasn't originally designed to do so well with HDTV. And for HEVC, I think some of the applications we're starting to see where HEVC is more being deployed are things like 4K and UHD resolution, and then a high dynamic range. Something else that's necessary for video codecs to be adopted frequently is how they're integrated inside of systems layers and by industry groups. Most other specifications need to be used along with video codecs. For systems integration, things like transport layers, MPEG 2 transport stream, MP4 file format, HEVC, the image format. These are important ways of carrying video codecs. And then there's a lot of industry groups that make application specifications that are very influential in the industries in which they operate. There's a long list of some of the different forums or groups that are defining standards that use video codec standards that are specified. Now, AVC and HEVC have been broadly adopted by these other groups. There are some efforts underway now to add VVC and also AV1. Alliance for Open Media is trying to also get AV1 being studied by some of these groups as well. Coding efficiency is really the reason for video codecs to exist. And the reason why we develop new generations of coding standards is typically because we want the big improvement in coding efficiency. So it's the key advantage of any new codec, but it's very difficult to measure. Quality metrics are a whole topic unto themselves, which I don't want to get into here. But the key point I do want to mention is that there are a lot of factors that do affect quality. And it's such an important characteristic in deciding if you're going to adopt a standard. So how do you measure it? Subjective quality versus objective quality is a big one. And then among objective quality, there's a lot of metrics. PSNR, VMAF are some of the most common ones, but there exists quite a lot of others. And then the other characteristic really is the encoder that's used. What encoder implementation are you using to measure your quality? Are you using the reference software for the committee? So they tend to be very slow. All of the major video codecs have an available reference software encoder. There's also open source software that tend to be used very frequently, especially for X264, X265, broadly used in a wide variety of applications. On the AV1 side, the SVT AV1 is a newer open source software encoder that's optimized. And what products are used? There's a lot of end products that support this, the codecs. And then even there, what are the parameters? All right, are you going to do constant QP versus rate control? Has the encoder been optimized in the settings to optimize for subjective quality or for objective quality? Because you can get different results based on the criteria that you've set inside of your encoding. And then what is your configuration for reference frames? How far are the iframes spaced apart? What kind of prediction hierarchy is used? Is it a random access mode or a low delay configuration? These are some things you have to look at when you're looking at the coding efficiency. You've probably all seen graphs like this that are showing coding efficiency, where the x-axis is bitrate and the y-axis is PSNR or another objective quality measure. And in a case like this, up and to the left is good. That means better coding efficiency, lower bit rate for the same quality or better quality for the same bit rate. This graph and most like it were generated using constant QP, with the curves formed from multiple different QP points. And this is just showing the progression of each new generation of MPEG codecs. But my point in showing this is to show that in this case, constant QP is generally used. But when we say constant QP, we don't mean just one QP value, but a set of QP values that go over a range. And if you're going to compare quality of two different codecs, you're going to get a very different result if you tried to say like a bitrate difference if you're at a different part in the curve. So video codec curves often have like a knee to the curve where there's a steeper portion and then there's a flatter portion. And so you're going to get a different assessment of how good a codec is versus other codecs depending on where on the curve you look, which is why it's common to do, they call the Biontech delta or BD rate, where 4 different bitrate points are used, 4 different QP values, and a curve fitting is done, and then an average over those points is used. When comparing coding efficiency, the encoder used is very important, and in particular, how good is the encoder and how complex is it? While decoders must support a full tool set defined in a profile, encoders are free to decide which tools to enable. And the available encoder implementations may vary in coding efficiency and the performance in the runtime, because the encoders can have modes that they set. If they set a choice to be running at a faster speed, they might get something very different results than if they're set to optimize coding efficiency, even at the expense of a slower runtime. So, your low complexity modes where you want to get the encoding done as quickly as possible, they will tend to eliminate certain tools or search options. Encoders have that choice. And if you're willing to be more complex, to throw more compute at an encoder, it can do a better job. The other thing is that over time, the encoder implementations for a given video codec standard do tend to improve encoding efficiency. And services may choose to deploy a new codec with that expectation that that coding efficiency will grow. So they might say, okay, here's a new standard, and the encoders that are on the market right now are not showing that much of a gain compared to the previous generation standard. But this is just a first generation encoder, and it will get better and better. And that's typically what happens with encoder implementations. They get better over time as Moore's law allows us to have more compute power to throw at the encoding, and also just we get smarter at designing our algorithms. This graph was provided by Fraunhofer HHI in a presentation about their VVenC encoder, and it's illustrating multiple different modes. So the x-axis here is the encoder runtime, and the y-axis is the PSNR measured by BD rate. And so this encoder provides multiple different modes. So they're comparing it to the HM, which is the HEVC reference software, and the VVC's reference software, the VTM. But then they provided 4 different versions of the encoder, and for each different version of the encoder, they showed it at multiple different operating points. So they're showing slow, medium, fast, and faster. So this graph illustrates both the new generations of an encoder do better because they start having better coding efficiency with better runtimes. And then they also show that even within a given generation of encoder, that you can choose to operate at a variety of different points along the curve. This graph is somewhat similar, but for AV1, and it's showing coding efficiency comparison at different software speeds using the SVT AV1. It's also being compared to libAOM and libVPX X264 and X265. But you can similarly see that there's a variety of different modes. So again, x-axis here is encoding time, and then y-axis is a BD rate using PSNR. But you can see that in the different operating modes, so if we look at the blue here of the let's look at the red with this SVT AV1, you can see that there is multiple different operating modes, allowing you to have different speed and different coding efficiency. In this graph, lower is better. During the development of a video codec, the coding gains achieved by the draft version of the standard can change pretty significantly during the development. So MPEG meetings are held 4 times each year, and this chart is showing, this graph chart table is showing the gains for each version of the reference software. So every time a new meeting was held, there would be a new version of the VTM reference software released that incorporated any tools that were adopted from that meeting. And so this is showing kind of over time the gain increasing meeting cycle by meeting cycle. And then also there's being the effect on the encoding runtime and the decoding runtime. Now, software encoding runtime is a very imperfect measure of coding efficiency and hardware complexity, but it's what we have as an objective measure, and so it does still get used. And you can see over time, the encoder and decoder runtimes, they started getting worse and worse, and at the end they got a little bit better as more efficiency was done. And this table is also showing the difference between gain on UHD content and HD content. Generally, at least with the newer codecs, it's easier to get coding gains on higher resolution content than on lower resolution content. So we're seeing, more than a 5% difference in the objective gains that were achieved on the test set. While trying to assess coding efficiency, you have to realize that there's a huge dependency on the content that's actually being coded. Sometimes people at Intel will ask me, oh, how much bitrate do I need to encode HD video or 4K video? And my answer is always that it depends on what the content is. Is it a video game? Is it video conferencing? Is it sports? Just different types of content can be very different. How much detail, how much motion, what's the activity level, what's the noise level, etc. And so if you're assessing, how good a codec is going to be for your particular use case, it's really important to test it on your type of content. Your content of interest at the resolution and the quality range that you're interested in. And so objective results such as the BD rate, use that multiple rate points to do it in a single number. And as I said before, the position on the curve above or below the knee has a very significant impact on how much gain. And it's hard to improve coding efficiency actually at the higher bit rate and higher quality levels. If you're on the steeper part of the curve, it's easier to have bigger gains. But there in the flat part of the curve where content is being very well represented, it's actually very hard to get coding gains. For a given target bit rate, the optimal resolution might vary. There's a lot of studies done of these Pareto curves trying to say, okay, let me try to find on this convex hole the very best position of bit rate to get the best quality. And the encoder performance and runtime is also content dependent, so not just the coding efficiency, but how long it takes your encoder to run can be very dependent on the content as well. To illustrate the effect of content dependency on coding efficiency, this slide and the next one, I have a little bit of a comparison. So this is from the VVC Verification Test results. And the x-axis is bitrate and the y-axis is a mean opinion score. But this is a result there were 5 sequences, 5 UHD sequences that were tested. And the 3 curves here, we have the HM, the HEVC reference software, the VTM, which is the VVC reference software, and then also the VVenC encoder. And it's showing like a 43% gain for the VTM encoder over HEVC's reference software, and about a 49% gain for the VVenC. So that's over 5 sequences together. But now let's look at the results per sequence. These are for 4 of the sequences. And if you look at them, you can see fairly significant differences on a per sequence basis versus what you saw from an individual basis. If you look over, for example, the metro sequence here, the gaps between the HEVC and the VTM are not as large. But if you look over at the meridian 2 sequence, there's a much bigger gap between the gains of the VTM versus the HM. I mentioned before that the encoder that you use can have a pretty significant impact on the coding efficiency. But when you're considering whether or not to adopt a new codec, just the implementation complexity of that codec is actually very important. And both the decoder complexity and the encoder complexity are important. So sometimes we use the encoder and decoder software runtimes as a complexity metric. I had the table before based on the VTM. It's a very imperfect measure, but yet it is used. And one of the biggest reasons why it's used is that it's available and it's at least somewhat repeatable. That when I say somewhat, if different compute clusters, we tend to run these encodes on compute clusters, and they don't tend to get the exact same result from time to time, but they tend to be fairly similar. And so when you do a comparison of like an A to B, this reference software versus the other, it's important to use the same compute cluster in both cases of the comparison so that you can get that comparison. And then the runtime, especially for the encoder, is highly dependent upon the software implementation. And was the software done in an optimized manner, making use of all the parallelization instructions available, or was it not? It can have a big impact. And so when we try to assess the complexity, there are some metrics that tend to be used. And so during the development of the standard, there are certain metrics that are used to assess an implementation in independent decoder complexity. Here's some of the metrics that are actually used. Worst case number of operations per luma sample, the number of multiply accumulates per sample, and then memory bandwidth is always a huge thing. That Moore's law has improved our coding efficiency over time, but it has not improved memory bandwidth very much. The total amount of local and global memory is important, and the number of line buffers that are needed to be required. And then, is an operation inherently sequential in nature, or can it be parallelized? Because those operations that inherently require to be sequential, you can't just speed it up by throwing a little bit more hardware at it. There's just inherent limits. Some of this I got from a paper that's listed here from Transactions on Circuited Systems and Video Technology, and I took a quote from it that I liked, which is, it says, that can be reasonably said that a VVC decoder requires about 1.5 to 2x the computing resources of an HEVC decoder. So as you have each new generation of video codec, generally the complexity increases, and more attention is paid in the standards body to decoder complexity than to encoder complexity. And that is because the decoders are required to support that entire profile. The encoders over time can do a better job and improve. But decoders, once you deploy the decoders, you don't want to make any changes. So that's an important characteristic that people look at when they decide if they want to adopt a new codec. Is the complexity reasonable that I can afford it for my usage? Now let's talk about the elephant in the room for video codec selection, which is patent licensing. The MPEG and the ITU-T standards require what's called fair, reasonable, and non-discriminatory, or FRAND, licensing of patents. For AVC, there was a single patent pool ultimately, and generally I think industry considered the costs to be low, to be reasonable, and so AVC has been very broadly deployed. HEVC has multiple patent pools, and there's a number of companies that are not in any of the pools, and the costs are indeed higher than AVC. And there's a lot of discussion concerned that the HEVC patent licensing situation has had an impact on HEVC deployment. And HEVC deployment has been slower and less than what might have been expected. And there's a lot of expectation that patent licensing rates has been a reason for that. Now, Alliance for Open Media has had a goal of being patent royalty-free, although I should mention that CISFEL has announced a patent pool and terms for an AV1 licensing. Alliance for Open Media, however, has responded that they established a royalty-free patent licensing commitment from all AOM members for AV1 implementations and completed a comprehensive evaluation of the video codec patent landscape and performance of patent due diligence. So we'll kind of see where that ends up. And then there's also a lot of questions then, what is going to happen with VVC patent licensing? But for HEVC, this is a slide that Jonathan Samuelson had provided that shows kind of the breakdown of HEVC patent licensing with the pools. That there are 3 pools that were established for HEVC, MPEG LA, HEVC Advance, and Velos Media. And then there's another number of companies that are not in any of the pools. I'd shown a graph earlier from the VVenC TV research report, and this is another from that same report's executive summary. And it's showing the combined MPEG family and Alliance for Open Media family codecs. And the MPEG family still has the higher usage, but by the end of the decade, 2030, it's showing the HEVC, the AOM family starting to cut into it pretty significantly. And this report specifically points to the patent licensing situation as a reason for this shift. Now, this is a forecast. We looking out pretty far, so we don't know how accurate it will be. Patent licensing for VVC is still uncertain. The Media Coding Industry Forum, or MCIF, made an effort to do a patent pool fostering that took place over the end of 2020 and the beginning of 2021. It got a very significant participation, 49 participants from Asia, the US, Europe, including most of the top contributors to VVC standardization. This effort had a goal of achieving consensus on a single patent pool for VVC. Ultimately, the group was not able to come to a single recommendation, but found significant support for 2 different patent pools, those administered by MPEG LA and by Access Advance, which was formerly called HEVC Advance. Both of these pools have announced formation and issued call for patents. So now it's time for conclusions. We've talked about that there's many different video codecs, and there's more expected in the future given the work that we're seeing going on of continuing to improve coding efficiency. But once a standard is actually completed, then there's a lot of work that remains to build the products and the services utilizing those standards. I've been involved in a lot of that work myself over the years, not just of contributing to building the standards themselves, but then building products that are using those standards. But many factors go into the decision about what video codecs to deploy, and I've tried to talk about a number of those in this talk. And another point I want to make is that it's really a decision about which codecs, plural, instead of a single video codec to deploy. That if you're implementing a new service, you can't just one day decide, oh, I'm going to turn off the old codec and turn on the new codec, because you need to wait till there's enough deployed products, especially decoders out there, a sufficient body of them before you can get rid of another codec. And so there's this whole decision often of how many different codecs I can afford to support in my service. And that concludes the talk, and now it's time for me to take questions. Thank you. Please ask your questions now.